good afternoon, wherever you are. Hope you are doing well. Please confirm if the sound is working. Should be okay. Good. I'm gonna close this, and we will open the course. Here we go. All right. So, good morning again, everyone. Uh, hope everybody is doing well. And we're gonna start the lecture today. We're gonna finish also the reg edit, the last part that we didn't do last time. We're gonna talk about memory buses and the schedule process on the CPU today, and we will end up with the firewall. All right, so this is our subjects for today. Where is my whiteboard? Whiteboard. Please don't forget to turn on your cameras and put your real names in there for the attendance. Okay. All right. So there is in Moodle already a new chapter in there. Please just refresh and you're going to find chapter 3, memory expansion slot and IRQ and firewall and SSH. Well, SSH, we already did that last time, but there is a lab at the end where you're going to work with the firewall and review the SSH also. So this is why it's mentioned on that title of the chapter. Okay, here is my screen. And here is the content of the chapter 3. So once you download the PDF, you're going to end up with this file. All right. So memory, we already know some few things about memories, right? We know that there is a storage memory like hard drives, memory stick. We can store in the cloud now also. We know that there is a random access memory that's dynamic, working in between the storage and the CPU, somehow in the middle. And also on the other side of the CPU, we have that SRAM that is static random access memory. And here, you're going to find the two main categories of the memory here. So we can go with RAM and ROM. We have the read-only memory, and who can give me an example about the ROM, random access memory? Happy Diwali! Yeah, happy Diwali, everybody. By the way, right? Happy Diwali, everyone. By the way. All right, BIOS, CMOS, BIOS. Be careful, CMOS is not ROM, CMOS is a RAM, right? CMOS is a RAM where we're gonna load that content of ROM on that RAM to be able to custom things, right? We explained that last time. Be careful. Okay, Kamaldeep. The CMOS RAM, we call it CMOS RAM. So it's in this category here. It's on a RAM. It's not in the ROM. The ROM can be PROM, EEPROM, EEPROM, the chips that we talked about, and we did an improvement till we have now electrically erasable. So we can erase the content and rewrite a new firmware or microcode inside electronically, right? So electrically, by the way, we use a software, and that software that is provided by the manufacturer, and so on and so on. So BIOS is a good answer, right? So we can have BIOS here on this category here of RAM. On RAM, we saw already two kind of RAMs, right? We saw a RAM, the regular RAM, but it's called DRAM, dynamic, and the other one is a static. Which one is faster here? Which one is faster between? We talked about that also last time. Between the RAM and the SRAM, or DRAM and the SRAM. Of course, SRAM. SRAM is much more faster. SRAM is for caches L1, L2, L3. Okay. So as you can see here, SRAM, we end up with the cache L1, L2, L3. Which one is faster here? Comparing these caches here, which one is the fast one? L1, good. Which one is the biggest one? L3, good. All right. So what is the difference now technically between the SRAM and the DRAM? Faster, costly due to transistors. Yes. So this one is more expensive, of course, but it's faster, right? So we can build caches with. This one is slower. It's not slow, it's really fast, but compared to the SRAM, so it's slower, right? But it's cheaper. And due to what? What is the technology that we are using on these dear capacitors? Good, capacitors. So this one is built with gates, flip-flop gates of transistors. And this one is capacitors. We have capacitors here, all right? So the charges are stored on the capacitors. All right, which one need consume more energy than the other one? Which one consume more energy than the other one here between the DRAM and the SRAM? DRAM, be careful. Ankush, it's not SRAM, it's DRAM. The DRAM need continuously refresh. Remember, guys, even to do nothing, just to keep the data inside, we need to refresh that RAM. Okay, we need to refresh that RAM. Well, this one consume less because of why? Because of we need a refresh just on an instruction of read or write. Right? So when we need to read or write, we need a refresh on the SRAM, but this one need continuous refresh, even if we are doing nothing in there, right? So just keeping the data inside, we need that electrical refresh. So this one is more consuming than the SRAM. Okay, so the DRAM is much more consuming than the SRAM on electricity. Okay, because it's based on those capacitors, and the capacitors, to keep the charge inside, they need continuous electricity. Okay, not like this one. We already have the charge on that flip-flop gates, and it's okay. So when we need to release that charge, that data, or that 0 or 1 or whatever, to read or to write something inside, well, we need a refresh signal, a refresh electrical signal on that gate. That's it. Okay, so we need a refresh on the SRAM just when we do something, when we read or write, when we have an instruction. In this one, we need continuous refresh, so it's much more consuming than the SRAM. Okay, good. Now we're going to talk more about the DRAM here, right? So we saw the caches last time. We talked also about the BIOS, even if we're going to do a little review here about it. But we're going to talk more about this third one here now. Okay, so DRAM, dynamic random access memory, it go with the stick bars, right, of RAM, and we plug them on the, what is the name of those slots? Well, we talked about that also last time when we studied the motherboard. They have a name. They have a name. The slots where this memory chip go on the motherboard, they have a specific name in there. What was the name of those ones? Expansion slot. Not really. They have a specific name. All the slots are expansion, right? DIMM, good. Mitwa, it's DIMM. Okay, Tarampreet, it's DIMM. DIMM, dual inline memory modules or we can use single inline memory module, right? So we have one memory module at the time, all right? So it's DIMM or SIMM. And even those RAMs here, we can call them DIMM, right? DIMM RAM, referring to the slot where they go. We have also microDIMM, that they are specially designed for the small devices like laptops, right? So SODIMM are the normal ones. SDRAM, DDR, DDR3, DDR. We're gonna talk about those DDR, DD something, right? And those ones also go for small, much more small devices. Okay, they are designed on micro size. We call them microDIMMs. Okay, the ROM is good for the BIOS. We have a BIOS, just microcode. What the BIOS do, by the way? What is the main job of the BIOS? Why we have that BIOS on a computer? He boot the computer how, Harkirat? Post, good Toyash, post. He do the post, and after it's the bootloader, Davinder. Yeah, good. Right, so we have a post that refer to power on self-test. Power on self-test. So you're gonna check all the hardware first and see that everything is working well. Okay, the synchronization between the component inside and so on. And after he will boot the operational system based on the configuration that he have, which is the first boot, can be the CD-ROM, can be the network card, can be flash drive, can be the hard drive, of course, right? So he's gonna look for that boot sectors where they are, and he will initiate the process of booting a system. Okay, this, of course, after the doing the post, that is power on self test, checking for errors first. If there's an error, if there's something or any part of this hardware stuff that it's not really working properly, he will warn us that there's a problem with the RAM, there's a problem with the hard drive, something missing here, right? So he's gonna warn us on the screen, and also with what? Something that we can listen to it. Beeps, yeah, beeps. Okay, so you're gonna use beeps. If all is good, well, we're gonna have beep, and the computer gonna boot normally. All right. The type of the chip where the BIOS is stored is called PROM, Programmable Read-Only Memory, and we upgraded to EEPROM, Erasable Programmable Read-Only Memory, and after we upgraded to the EEPROM, that is electrically erasable, right? Because this one was erasable, but with a specific process and only the manufacturer was able to do it. We needed the ultraviolet process of light and so on. And this one was by replacing the chip completely, right? So we removed the chip and we solder a new one in there. And this one, we can just use a software to be able to update that microcode that was stored on that chip. Okay, now the RAM. Of course, the memory, all the memories have this specification of speed. The memory have some speed. They're really fast. Talking about 2 nanoseconds to 80 nanoseconds per operations, right? And they have a CAS latency that we're going to talk about it. It's column address strobe. This is the time between looking for something on the memory and that thing is already available on the data bus. So the time in between is called latency. It's called the latency. It's parameter that is really important when we refer to the RAM. So RAM, random access memory, temporary storage. Is it volatile or not? The RAM. Is it volatile? Yeah, good. And what about the BIOS now? Is the BIOS volatile or not? Non-volatile. Okay, so the BIOS is Non-volatile. What about the SRAM? So here we are talking about the DRAM, right? What about the SRAM? Is the SRAM volatile or not? Yes, no, yes, 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 yes. Okay, there's more yes than no's, right? Of course, it's a RAM, SRAM, RAM, it's volatile. Okay, so even if it's static, it's just the way that we are storing data inside and the technology that we are using, and it's fast, right? But it doesn't mean that it's non-volatile, right? The EEPROM, uh, the data is printed on the circuits. Okay, so this is why it's non-volatile. Okay, so even if you have no electricity at all, well, once you're gonna charge on electricity that circuit, you can read what's already inside because it's already printed on the circuits, right? But RAM is just like drawers that we can put things inside, but when there is no electricity, those drawers are empty, right? Okay. Now those drawers, they can be digital security with fingerprints, something, or they can have keys, or they can, but depend on the technology in there. But once there is no electricity, those drawers are empty. Okay. But the ROM is different. So the data is already printed on the circuits. All right. It's printed on the the circuits. All right. So the RAM is volatile. By the way, volatile means that it need a continuous refresh to keep the data. When there is no electricity, the data is gone forever, right? So this is the RAM. Whatever, SRAM, CMOS RAM. This is why we have a battery on the motherboard, right? CMOS RAM. So it's RAM. It need electricity to keep the data, right? So this is why we put that battery to keep the informations of the CMOS RAM on that CMOS RAM. All right. So we need electricity to keep the data. So this is a volatile memory, right? SRAM, DRAM, both are volatile. Okay. So it's a temporary storage. Temporary storage, meaning that once the computer is turned off, everything stored in is lost. It's volatile, right? See, computer turned off. There's no more electricity. Data is gone. Data is gone. When an application is opened, it's copied into a RAM first to be processed on the CPU. Okay, so basically it's on storage space, flash drive, hard drive, whatever. It will be copied on that RAM and it will be processed on the CPU after. So we have two type of RAMs, dynamic and static. So dynamic is the main random access memory that we have on our computer. Okay, bigger, slower, cheaper, capacitors, volatile, right? SRAM, smaller, we can build caches with L1, L2, L3, okay, more expensive, much faster, and smaller, all right? Both are volatile. Now what we have in this RAM here, we have banks. You see, banks are type of chips we have in here. They are soldered on this stick here, and we have pins that they're gonna plug on that slot that we call DIMM or SIM, of course. So RAM, random access memory, stored on the motherboard in modules that are called DIMMs, dual inline memory module. They can have several amount of those pins on the bottom here, right? 168, 184, 240, 288 pins. Those are the pins, right? SRAM do not allow bigger amount of memory. Now we can they compare to the RAM, they are much more slower, right? So they are on kilobytes or megabytes just for the cache of the CPU, just for the caches of the CPU. Well, the RAM, the DRAM, it's on gigabyte. It's on gigabyte the capacity. But the SRAM, the caches, they are just on some kilobytes or megabytes. For the L3, some megabyte. L1 is on kilobytes. What the RAM do, see, I have the RAM here. This is my hard drive. And those disks here are softwares. Let's say that those disks here are different softwares depending their colors, right? So you see that we have a tunnel here exchanging those softwares between the RAM and the hard drive. So we load those softwares on the RAM. They are processed to the CPU. CPU give back answers, and we store back on the hard drive, and so go on. Okay, if we need that. Okay, so we have a write back here. So it's kind of a middle process here between the CPU and the hard drive. So in order for a program to run, it need to be loaded into the RAM first, into the RAM first. So CPU to be able to process any data from your hard drive, it will be loaded on the RAM, and after it will be processed. So here we have exchanging those the process and writing back to the RAM here. And if we need to save something, definitely, so we save it back here on the hard drive. Require constant electrical power to store data. Well, we already know that. Okay, continuous refresh, because it's capacitors. And capacitors are kind of buckets here that they're gonna have tiny holes, and if you're gonna fill them with water, this hole will always drop this water, right? So there's always some amount of energy that will be lost, and this is why to keep certain amount of charge inside those capacitors, we need continuously dropping that energy or that water if you want, right? So I have a bucket that have a hole on the bottom, and to be able to keep a certain level of water on that bucket, I need to continuously keep putting water, right? So this is a continuous refresh to keep the data inside. DRAM, dynamic RAM, contain capacitors. Capacitors have to be refreshed with electricity constantly. Okay, compared to the SRAM, SRAM is not constantly. It's when we read or write. We're gonna send the signal, electrical signal, when we need to read or write. RAM, SRAM. Now be careful. We have some new thing here, and usually students are mixed between. So what we just saw, we saw something called SDRAM. We didn't know this before, or did we know it? Is it SRAM? No, it's dynamic, right? So we still have the D here. So be careful. SDRAM is not SRAM. And this one is not equal to this one at all. Well, this one is a static. And we can have caches L1, L2, L3. DRAM evolved to this one. So we had a DRAM, and after it's kind of an improvement of it. It's called synchronous. This is what we just saw here. Synchronous. Synchronous. What is this? It's a new thing, right? So this synchronous RAM work better because it's synchronized with the frequency of the motherboard. So this one have the same frequency of the motherboard. It's synchronized with the frequency of the motherboard before working. All right, so it gives us much more better management on reading and writing and the speed. Okay, so we had the RAM first, and this RAM can be DRAM or can be SRAM. So the RAM, the main one, can be dynamic or static. The dynamic one was being improved to synchronous dynamic RAM, right? Synchronous dynamic RAM. So the frequency of this DRAM is synchronized with the frequency of the motherboard. Used today in the DIMMs. Well, the DRAM operate asynchronously with the system clock, the frequency of our motherboard, the clock of the system, the RTC, real-time clock. And the SDRAM operates synchronously with the system clock. All signals are tied to the system clock for a better controlled timing, and this give us much more advantages on the speed. All right. So we had RAM, DRAM, SRAM, DRAM, SRAM, right? Static, dynamic. On the dynamic, we had after synchronous. It was being synchronized with the system clock. Okay, with the frequency of the motherboard. RAMs, they have notation, right? So as you can see here, we have some capacity. 128 megabyte, it's not that much, right? It's SD-ROM, old one, right? Deprecated. Don't really use SD-RAM now. We did other improvements, right? So this one was the first improvement here that we were able to work synchronously with the clock of the system. Okay? So that was the first improvement from this DRAM. We get DRAM, and after we were able to work synchronously with the clock of the system. We called it SDRAM. Well, we can have here 32 gigabit of SDRAM. This one is good on capacity. We have 32 gigabit on SDRAM. DDR1. What is DDR? DDR is double data rate. Double data rate. How things work here. Now, you see this SDRAM here. It was good because it works synchronously with the motherboard, right? So SDRAM. And what we did to it after, so we got this SDRAM, we had that frequency, right? So it's not really here. So this one is equal to this. But after we took this one and we doubled the data rate, double data rate. This is DDR, right? DDR. What is this doubling data rate mean? We had the frequency, right? So we had a frequency on the RAM. Okay, let's say this is my frequency. And this is synchronized with the clock system. Okay, good. So going from here, and on some interval of time, I will go exactly to the same place. So this is one cycle. This is a second cycle in the same amount of time, right? Let's say this is 2 nanoseconds or something in each one, right? So this is positive age and this is negative age, right? So this is positive edge and this is negative edge. And on those edges, the frequency here, positive and negative, positive, negative, and so go on and so go on. When it was SDRAM, we were able to do an instruction in each cycle, right? So this is one cycle. I have an instruction, so it can be 0 or it can be 1. I have an instruction, it can be 0, it can be 1. I have a cycle again, can be 0, can be 1. So I have here some data that is interpreted by each cycle. When we doubled the data rate, we were able to use these positive and negative edges. So we double it. In each cycle, I have two signals. In the positive can be 0, 1, negative can be 0, 1. Positive can be 0, 1, negative can be 0, 1. Okay, so in each cycle, now we have kind of 2 bits if you want, right? Because now we split it one cycle by 2. We have this positive and we have this negative, and we can control more of sending data on this positive and negative edge of one cycle. So what we did here, if I had some cycles, I have, for example, 3 cycles. Before, I have three cycles with the 3 instructions. Now, using the 2 edges of each cycle, what I'm doing, I'm doubling the data rate, because in one cycle now I have 2, right? So this time 2 using the DDR. All we did, this is from where the name come of double data rate. Before we had the SDRAM, it have some data rate, right? In each cycle we have an instruction. Good. Now in each cycle we have 2 of that, right? So in some frequency that I'm gonna have, I will double the data rate. I will double the data rate, and this is from where we get the DDR. This is from where we get the DDR. DDR. The notation of the RAM usually is this. When you find PC, and after you're gonna find the frequency here, right? So you can find here DDR1, for example, or you can find PC100. If it was DDR2, you're gonna find PC2. DDR3 is PC3, and so go on. As here, as an example, 100 is the frequency, so 100 megahertz. See the speed at which it operates. And imagine I have 8-byte wide bus. So the bus is 8 bytes. It's gonna be 100 times 8. That it's gonna give me the speed of this memory. It's a 800 megabyte per second. So I can transfer 800 megabyte per second, because I can transfer 8 byte at the time, but I'm working at 100 cycle per second. This is 100 megahertz. 100 cycle per second. Then each cycle gonna have 8 byte, the width of the data, right? So 8 times 100 gonna give me 800 megabyte per second. This is the real data rate of this one, right? Now this is what I was talking about, the data rate. See, I have some frequency here, and I have a single data rate. See, in each cycle, data. Each cycle, data. Each cycle, data. DDR in one cycle, I have 2 data. One cycle, data, data. One cycle, data, data. So I'm doubling it, right? It's kind of this one. If it was double data rate, 100, it's gonna be kind of in here, instead of 8 byte, I'm gonna be able to transfer in each cycle of this 100 16 bytes in reality. So it will be 16 times 100. It will be 1,600 megabyte per second, right? You see the speed, it's the same. I didn't change it. It's the same frequency, 100 megahertz. But instead of transferring 8 byte, I'm transferring kind of 16 if you want, because I'm transferring the double of it, right? So it's not 8 anymore. It's 16. So here it will be 16 times 100. Well, this is the idea in behind of the doubling the data rate. Now DDR2, what is the DDR2? DDR2 is an improvement of the frequency. That's it. So we already have synchronous first as DRAM, and after we were able to double the data rate using this technology of doubling the things. And now we will just play with the frequency. So instead of here, for example, well, let's say this is 20, right? 20 nanosecond. And I'm gonna play with this frequency. Now in 20 nanoseconds, I'm gonna have 6 cycles, right? So this is the improvement of DDR2, right? So playing with this frequency, higher frequency, much more a higher frequency. Okay, so I will have one cycle here in 2 nanoseconds, for example, because I'm having 10 or I'm having 5 here, right? So it's 20. So I'm having 5 here of the cycles. I will have one in each 2 nanosecond. Of course, what I'm doing here, I'm having more speed. I'm having more speed, and this is how the memory is working now. So always we are trying to improve that frequency and that speed. So DDR2 is faster than DDR because it allows for a higher bus speed, a higher bus speed. It has 240 pins compared to DDR 184. What we have here 164, also 180. And you see the notation, it's a DDR2 800 megahertz or PC2 now with the frequency. See, PC2 is for DDR2. PC is just for DDR, as we saw it here. PC. PC3 is for DDR3. Okay, DDR3 is much more higher speed, of course. That's it, right? So the bus that is using is an improvement of the DDR2, so we can have higher frequency on the time. So DDR3 twice as fast as DDR2, also have 240 pins. Bottom notch are in different place. So you see we have notches here that they can make a difference in between. DDR and DDR2, they have exactly on the same place the notch that it will be plugged on that DIMM. DDR3, see, they have the same amount of pins here, but the notch is totally different. It's on the other side. Now, when we can see it, we can see the notation here, and we can see the notch place. We can say that, okay, so this is a DDR3, right? So they don't plug in the same DIMMs. The DIMMs are different. Is data an organized form of energy? Yeah, we can say that, Sheikh Mohammed. Yeah, organized form of energy if you want. Well, yeah, we can say that. So we organize that form of energy, not just organize that form of energy, even we organize how we process that energy that we organized also. So even the process is organized. This is coding, so we code it. We code that energy. Okay. It's not really the energy in itself. It's the coding that is behind that form of energy, how it's organized. Well, this is a better explanation, I guess. Okay, so it's more the way that this data is organized and it's coded to be processed. This is the data in reality, right? But if we go to really low level, it's just energy, of course, right? So it's a electrical signal or whatever signals. All right, can be radio, can be light. Radio is also an energy, right? So it's electromagnetic waves. We can say that light is photons, right? So it's energy also. If we go to low level physics, understanding things, right? But it's more that way of proceeding this energy and how we encode So it's organized. Okay, well, we can just organize one on top of the other one. It's still organized, but how it's organized and how it's the process to deal with this organization in behind this is the data. This is the coding, right? Because we don't need just an energy, or we don't need just a energy. Energy is energy, but how we organize and how we process this organization also. This is how we code it. This is the data. How we end up with data. So DDR3 2 times faster than DDR2. You see the notches now. We have notches that they are in different places compared to the technology and the form of the DDR. DDR4. DDR4 is mentioned as DDR4 here, or can be mentioned also as a PC4, PC4, right? We're gonna find some capacity in there and has 288 pins. 288 pins offer a higher range of speed than DDR3. Of course, now we have also even DDR5, guys, that was being released on the last July, right? So it was being released on this year officially. I mean, that was DDR5. It's the same concept, right? So it's doubling the rate, not really doubling the rate, doubling the speed, if you want, right? The bandwidth. This is the real term of it. So it's not the data rate, because we already doubled the data rate on SDRAM, right? So it's already using the double data rate technology, but we have much more bandwidth on the bus, and we end up with the double speed of this DDR4, that we call it DDR5, and it was being designed also to consume less energy than DDR5, right? So we higher the speed and we try to consume less energy. This was being released on the last of July of this year. That we call it DDR5. Type of slots. Oh, we can have Rambus, we can have SIEM and DIMM. So single inline memory modules. See, the pins are totally different also. And dual inline memory modules here can go from 168, 184. This is DDR1. Here we have DDR2, DDR3, and here we have a DDR4. Rambus is older type of RAM, right? Let's call it the Rambus inline memory module. You see that the RAM is totally different, usually used on servers, and usually it have two notches, right? Two notches. Right, same characteristic. It have some capacity and it have some speed and different amount of pins also, right? I use mainly on servers this one in some type of machines that we call RIM, right? But the basic one is this one that we are using nowadays, dual inline memory modules called a DIMM. Okay, it's called a DIMM. Those chips here, they're called memory banks. Memory banks in each one. Okay, and they all belong to the final amount of capacity of this RAM. Electronically called TOD, I guess. Well, it's just for me, right, to remember that. So yeah, that's it. See, thin, small outline packages that we use on a memory, or usually we call them TOP. So the type of the chip, exactly, electronically talking, right? All right. So Not RAM memory stick come in the following size. So this is much more deprecated here. 1 GB, it's really low capacity. 2 gig, well, you can still find them maybe in some computers. 4 gigs and 8 gigs, 16 gigs, 32 gigs. We have even 64 gigs now, right? In one stick. We have tell 64 gigs that they are some kind of expensive. Here you have some tables that I will let you check after, right? Some examples of speed of DDR1. This is the clock speed. This is the DDR speed rating. It's that the difference of notation. You see that it's always double because we are doubling the data rate, no more, right? So it's 100, become kind of 200s here. Okay, and 133, it's 266. See, it's the doubling the data rate, doubling the data rate. And the DDR2, so we have here the 100 that started with, double the data rate here, and double the bandwidth. So we end up with 200, and after we end up with 400, and so go on and so go on, right? So this is how the concept on behind is working. DDR3. On DDR3, we get some improvement here. It's called low voltage and ultra low voltage. So we have two kind of DDR3. One is DDR3L, DDR3U. This is for low voltage. This is for ultra low voltage. Why we did that? And what is it exactly first? So as you can see here, we are talking about the electricity and voltages, right? So DDR3L ran at 1.35 volt compared to the 1.5 or 1.65 volt of the regular DDR3. The ultra low voltage, it's less than that. Well, we can go till 1.25 voltage of consumption here. See? So why we are doing this? Well, what do you think that have an advantage? What is the advantage of this one? So with the new advancement in server RAM definition, there is now gigabyte modules also available in DDR3 2933. Well, 128 gigabyte in one module. Novi, it's in one module? Because I don't know. I'm asking you the question to learn. In one module, or you mean like 4 times 32 or double 64? Because this double 64, whatever, I know that we have it, but 128 on one, I didn't know about that. Maybe the technology improve every time. i9 one module. Okay, that's good. That's good to know. Yeah, Kingston made the module. That's great. Okay, that's great. All right, so Novi saying like we have now till 128 in even one module. Well, that's great. Okay, so we were talking about. I asked you a question here. We were talking about. You see the consumption of the electricity. So we had the regular DDR3 working at 1.5, 1.6 here voltage. And after we built some other kind of memory DDR3 that's working on 1.35. See, it's not really big difference here. Now we call it L for low voltage. And after we did also more improvement, and still not really big difference. You see 1.25, 1.5, right, for ultra low voltage. What is the advantage of doing this? What is the advantage of doing this? Low voltage RAM, more stable and less heat. Can be used to make on the motherboard stored on like Apple do. We can use them everywhere. not just used to make on the motherboard. Soldered. So I read that as a storage. They are for soldered on like Apple do. Well, no, not really. Not it's not. It's not really considered as an advantage or whatever. Even if they are soldered, is more about the reshaping and getting things smaller and so on. Yeah, sure. So it will consume less energy, but what is the advantage of consuming this less energy? See, it's 1.5, 1.25, and 1.35. See, it's not like we are consuming 100 watts kilojoule and we reduced that to 5 kilojoule or something. See, it's not that much, right? So, but still, they did it. Let's consume electricity. Yeah, of course. But I'm saying, what is the advantage of consuming less electricity on 1.5 to 1.35 and from 1.5 to 1.25? Or from here, look, well, I have a low voltage, and after ultra low voltage, well, it's uh, 0.10 millivolt, right? It's nothing. It's 10 millivolts here that I'm talking about. So you think that it's gonna have an advantage that you're gonna put this on your computers? I'll imagine that I have regular DDR here on my computer, and I will put DDR3, and after I will remove them, and I will put DDR3 ultra low voltage on my computer. What is the advantage of doing this for me? What I'm gonna win doing that? Speed? No. Low budget computers. Less heat generation and making compact device. So my computer gonna have less heating just by changing this 10 millivolt, and I will have a better compact device thing. If I'm gonna just go and buy some ultra low voltage RAM and change them on my computer. You think that I will see the difference? Good. This is what I was looking for, Bharat. It's for big data centers. Because of if you're gonna do this at home, you will not see any difference, right? Even your bill, the electricity, I mean, it will not have any difference at all, right? Well, maybe some few cents. It depends on the countries how they count the consumption. Well, but it's nothing for us. It's not for us. Imagine if you have hundreds of thousands of RAM running on servers in one building for data center. Now we are talking, right? Now we are talking. It's not a simple computer. My simple computer, I put DDR3 or DDR-L or DDR3 ultra voltage. The heating gonna be almost the same. I will not see it. I mean, there's less epsilon change in here, right? Because why? Because it's just one computer. But when you have a building of hundreds of thousands of RAM working on servers in the same time, now we are talking, right? It's gonna have a huge advantage on the billing dollars at the end of the month. Now, I'm not working with one RAM. I have hundreds of thousands that they are all working in servers 24 hours per 7 days, consuming electricity. So imagine in 1 year, right? Imagine in 1 year the advantage on that electricity bill that I'm gonna have, right? So those are much more built for data centers. data centers, as I say here, think big data centers like the one that power Google, for example. How many RAM Google is using, right? So how many RAM Facebook is using? How many RAM Amazon is using? So even if I have 1 millivolt that I can improve, at the end of the year, I will have an advantage improvement on my electricity bill, of course, even if it's 1 millivolt on that case, because I'm using hundreds of thousands of RAM running on servers 24 hours per 7 days, right? It's not really an advantage for us, because if I change them on my computer, I will not really see a big difference at all, right? Neither on dollars, neither on heating, neither on capacity, neither on whatever. It's almost the same, right? But data centers, this is other thing. This is other thing. All right. Okay, so you have here some speed of this DDR3. As you can see, we're still working with this basic of SD-ROM first, right? So you see, remember the DDR1 here when we doubled the data rate. We just go in with the SD speed. We double the data rate. So here we still with that SD speed first that we had, and we are doubling the data rate and 2 times the bandwidth and 2 times that bandwidth from DDR2 to DDR3, we end up with the 800. So the double of the double here, and after the double also on the bandwidth here, right? So we end up with much higher frequencies, and we can have a higher speed. DDR4, same concept. Okay, a 200, 266. Well, those are removed, started from here, and we have the 400 megahertz, and working with the double of the double of the double of the double of the double here logically, right? So we end up with this with these speeds here. Mention it as PC4, here mention it as PC3 for DDR3, and here mentioned as PC2 for DDR2. Latency. So we call it CAS latency, right? CAS latency. Latency is the time between when we send a request to the RAM in some location and this data is already available on the bus, right? So it's coming. Okay, this time in between, what we call it latency, that it's really important. But people usually, when they deal with the RAM, all they care about is the speed and the capacity, but they don't know that sometimes if the latency is high, they are still doing nothing, right? As you can see here, I give few examples. This is speed here, and this is a speed here. See, 166, it's all matter about the latency here. The speed is plain, but they have the same latency here. But you see this one, for example, if we take this speed, so it's less than this speed, right? If I take a memory with this speed, with the latency 7, so you see that I have a performance of 656. And if I take this speed with the latency 12, I will have 10 seconds on that performance, for example. So it's still this one with the lower speed better than this one 2 times. Why? It's not because of just the speed. Well, you have always to take care with this number that you're going to find on the description of your RAM, that is called latency, that we mentioned on the beginning here, right? So we have a memory speed, that is good. We take in consideration that speed, okay? But you always refer to that CAS latency to see if it's better, or because you can find some lower speed with higher latency that it's cheaper than the other one that it's high speed with the higher latency, and you're gonna just spend your money getting a higher speed with a bad latency on that memory, and you can buy cheaper with a better latency and a little bit lower speed, you're gonna have a higher performance in your computer. Colon address strobe here, that it's a parameter that is really important when you deal with your RAM. Right, so it's not just a matter of speed. Of course, the speed is one of the main characteristic of the RAM, the capacity, but this latency is playing a really big role here. As you can see on this table, we have many examples of the speed. So we go higher speed like this, and the latency is smaller or higher. Right. So as you can see, you find this one, for example, as 1600, and with latency of 15, it's exactly better than the 1700 with the latency of 16. And you can just come here and see the higher speed. All right, well, this one gonna be $60, and this one gonna be like $30, right? But you can see this one is much more performant than this one, without knowing, without taking care about this colon address store, right? So the latency is one of the factors that they are really important when you deal with the RAM. Big data centers. Okay, virtual memory. What is a virtual memory? Who can remind me what is a virtual memory? Is it the memory for the virtual machines? What is virtual memory? Paging plus ROM. Paging plus RAM. Yeah, good, Mitwa. Okay, it's not ROM. Be careful. Be careful, Harmander. It's not ROM. We're talking about the RAM, right? So the paging is that here, if we go back to this picture here, right? So we have that paging and swapping. So we swap things, and we have that space here for paging, and the concept of that space on the hard drive that it's gonna give more support, acting as RAM. That space on the hard drive is gonna be acting as RAM. This is what we call a virtual memory, right? So part of RAM for swapping. No, part of hard drive, not part of RAM. Because better to say part of the hard drive, right? Part of the hard drive. Well, you better just saying paging plus RAM, paging plus RAM. Okay, paging plus RAM. So this is the concept of the virtual memory. So we swap things in between, and we have the same concept between the caches also. Well, differently processed, of course, differently processed, but same concept, right? So we swap things also, and we keep trace of all those pages of addresses of the memory, and we have that virtual memory. But for sure, it's not the memory of the virtual machines, right? It's not the memory of virtual machines. This is what we all agree on, right? So be careful. Dual and 3-channel memory, quad channel, and so on. So what is this? This is something how we deal with the so we have a memory controller, right? We have a memory controller. We're gonna need a motherboard. So motherboard. See some good images here. There we go. All right, as you can see here, we have some DIMMs, right? And you see that I have 4 DIMMs in this one, 4 slots for the RAM, and this guy is just putting some RAM stick on the DIMMs, right? He's plugging them on the DIMMs. And what about these colors? What about these colors? See, here's another one here. Here's another one. I have some other colors, right? Well, we can see the two others here. I'm gonna find others for sure. Here we go. I have this one. See? What about these colors? What are you noticing about the colors here of the DIMMs? How they are? For GPU? No, we are not talking about GPU at all. What about the colors? I'm not talking about the channels yet. I'm just asking about the colors. You see colors, the rainbow colors, green, blue, red, white. So what about the colors here? What about the colors? Come on, guys. It's in front of you. What about the colors? Here's another one here. Where is it? Here is it. See colors here. There's something weird about these colors, right? Why they are coloring them like that? Improper location for optimal performance. Well, you still didn't get my question, Novi. What about the colors? Simple question. I'm not talking about channels, performance, whatever yet. What was in there for these colors? Same colors? They were all same colors, Chief? Same type of things in same colors. They are all the same type. If I'm using DDR3 in my computer, I'm using DDR3, so it's the same speed, same whatever. Same type of things. Which what is the different things? There's no different things in here. It's just RAM that I'm putting on my motherboard. But why they are different? Dual channel or single channel? Well, all right. On the RAM, we have that part of memory controller that was before on the North Bridge, right? But now it's included on a CPU. So we have here that memory controller interface, or MIC if you want, that it's now dealing just directly with the RAM, right? But before was the FSB, remember? It was the FSB, and we had that North Bridge, and North Bridge have included the memory controller, and here we deal with the RAM. Now the RAM, imagine that we have 4 slots. So I have this 4 slots, and as you can see, they put them on alternating colors, right? This is the answer that I was expecting from you, but nobody said that. I just asked what about the colors? They're alternating, 2 different colors alternating, right? So why we do that? Why we do that? So imagine if I have here for each channel, this is what we call a channel here in between, right? So for each channel, I will use a link. Well, let's say this is the green link here. So this is my modules, right? And I have that green. They have that green here. And I have that block exchanging data with the block here. Okay. Now, why they are putting these colors? To tell you that if you have one RAM stick, so I have one RAM stick, well, it's gonna go here or here, right? So I can put it in this one. Okay. But to be able to use, so you remember, so this is a memory controller, MC, and this is a memory controller, MC, that can read and write in this one. So this one is controlling this read and write here, and those are gonna go to the CPU. Okay, those are gonna go to the CPU. Well, now those ones are included inside. Okay, now what if I'm gonna have two memory sticks? And let's say that I put it the first one on the slot number 1. So this one is RAM 1, and I just plugged it here. Where is the better slot to plug the RAM to? So I just went to the shop. I want to upgrade my RAM, and I bought one of these RAMs, one extra, and I want to plug it on my computer. Where I can put this RAM? Where I can put this RAM? Like literally. So let's say this one is number 1, this one is number 2, this one is number 3, and this one is number 4. Same color channel, 3, 4, 4, whatever. One and 3. All right. 1 and 3. So I just said where I can put this RAM. Technically, the answer is I can put it everywhere. Right? Literally, where I can put this RAM, well, I can put it everywhere. I can put it on number 2, I can put it on number 3, I can put it on number 4 here. Well, it's not a good idea, right? But where is the better place to put that RAM? Now it's good to follow the colors. Right? Why? Because of, imagine this memory controller as a hand, right? So this is a hand, and I have just one memory controller. So I have one hand, and I'm just reading from a book, and I'm using my hand to copy the page. So I'm writing, right? So I'm copying the content of that book on my some paper, right? So I'm just taking paper here and I'm writing. I'm using one hand, right? I'm using one hand. This is my memory controller here. Okay, that's good. Now, if I'm gonna put this capacity in the same here, so what I did, well, basically I just made that book bigger and that page bigger, but I'm still working with the one hand. Right? So I'm having more data to write. I'm having more space where I can write, but I'm still using one hand on that space. So this is one channel that I'm using at the time. So it will be a really bad idea to put it directly on number 2, because I'm not taking the advantage of using two hands in the same time. What if now, instead of making my page bigger, I will have a second page and I will be able to use two hands in the same time. So I'm using a dual channel. So I have first channel here and dual channel here if I'm going to put my RAM on the number 3 and following the colors. It doesn't mean that if you're going to put your RAM here, it will not work. It will work perfectly. I can just take the RAM 2 and plug it here on the green, and it will work. Right? But not the better way. It will work the bad way. So I'm still not gaining on my speed, and I'm not using the advantage of using the two hands in the same time. But if I'm going to put it on the number 3 directly, I'm going to use the advantage of using the two hands in the same time. So I have double my power, my speed, my whatever, my capacity, whatever, right? So this is the idea behind of this colors of these colors inside. Well, technically, now we saw many RAMs working together. Let's talk about the memory banks, how they work. Because they are all separated also, right? So all those, we are not storing data on the chip in itself on the stick. We are storing data on those memory banks. And memory banks work with the pins here, and we have some bus. So let's do it on proper manner. Let's say I have a memory here. A width here gonna be 8 byte, right? So I can store 8 bytes in each location, and that will have several addresses here, right? So going from 0 hexadecimal till FFFFFF hexadecimal, right? So I'll go to the last probability here of addresses. And let's say I have 1024 addresses. So I have 1024 addresses on 8 byte, or let's make it more simple here. Instead of 8, we're going to take 1 byte. So 8 bits, right? 1 byte or 8 bits, just for the calculant to understand the principle, right? Okay, so I have 1 byte in 1024 addresses. What is the capacity of this chip? What is the capacity of this chip? 8 gigabyte? Seriously? 1 gig? Be careful. I have 1 byte and I have 1000 addresses. So how many addresses here I have? Not by bits anymore. Yeah, because I have 1024 probabilities bits. This is a kilo, guys. This is kilo, just 1000. This is just kilo. Why go into gigabyte and whatever byte? This is 1 kilobyte. This is 1 kilo of address. I have 1000 of address. So it's 1 kilo of address. Now in each address, I can have 1 byte. So it's going to give me 1 kilobyte. So this chip capacity is 1 kilobyte. It's 1000, right? It's 1000. And it's not 1 kilobits. Be careful, Harmanda, right? So this is different than this. This is 1 kilobit. If I had 1 bit per address, so I have 1 kilobit. If I have 1 bit per address, now I have 8 bits per address. So it's 1 byte, right? So I have here 1024 bytes, 1 kilobytes, right? 1000 meters is 1 kilometer. 1000 gram, it's 1 kilogram. Kilo is 1000. Okay? Kilo is 1000. So I have 1 byte per address and I have 1000 address. Well, I can say that I have 1 kilobyte. 1 kilobyte. All right? 1 kilobyte. Now, how those chips are synchronized. So imagine I have the same concept now, but multiple times. Well, let's take 4. Now I know that this one is 1 kilobyte, and in my chip I have 4 times that, So what is the capacity of this memory? $125? Seriously? I have 1 kilobyte per chip memory bank, and I have 4 times that memory bank. So I will end up with what? 4 kilobytes. That's it. So this chip is for 4 kilobyte. All right. Now, what if I'm gonna put exactly the same chip on the other side also? To the other side also, because this is my chip from top, and I'm having this 8 from one side. This is 4, and I can have the 4 in the other side, right? So on the back of this chip here, on the back of it, I can do the same thing, right? So I will have 8 kilobytes. And this is just an example with kilobytes. Now, the more you have addresses of the weights, right? The more the weights of the address bus is bigger, the more the chips are bigger. They will have more cells where we can put data, and the more the memory is bigger on capacity. The more memory is bigger on capacity. That's it, right? So this is how these memory banks are synchronized. Well, electronically, of course, we're gonna have a bus for data in and data out. We're gonna have a bus of addresses, and we're gonna have bus of instructions. As we said in the first module, remember in memory we have a data bus, and we have address bus that gonna have a lot of probabilities in here to select the location where we're gonna go to write something. So this is several bits here, depend the width, right? So this is our address bus here, and of course we're gonna have another bus that can be read or write, right? Can be read or write. Well, this one is just one wire that can be 0 or 1. So once we select here the address, so let's go here for example, and we're gonna send 0, we will just write something, and we're gonna send 1, we're gonna push the data out. If we send 0, so we select this address, the data is in, and this bus will be selected, then the data will flow in this direction, and it will be registered here and here and here and so on. Right. Selecting the addresses one after the other one, we put the data on inside. Okay. Now, also same way, if we gonna have this 4, we're gonna have the data in on each one. So what's gonna be the width of my input bus here? What's gonna be the width of it? So the input bus is going inside, right? And of course here we can just join them here. So how many wires if I have here 1 byte of data that I can store here in some addresses? What's going to be the width of this bus here of the input that where I'm able to send data inside the chips? What's going to be the width? Here I have several bits, right? So when we put 1 wire and do this means it's a lot of wires, right? This symbol electronically, this means it's a lot of wires, right? So instead of doing this, we do 1 line and we put this. Okay, so I can have 1 line with this symbol electronically. This means here several bits. I have a lot of them. All right, so let's say here I have a lot, and I have a lot, and I have a lot here, and I have a lot here, and I have a lot here. So what's going to be the width of this one if I have 1 byte here? How many wires I'm going to have here? Good. Davinder, good. It's 8. Harkirat, how the hell I'm gonna store 8 bits in one wire? You see, those ones are the cells that they are all linked to this bus. True or not? So this one gonna have 8 to have 8 bits to be able to build my 1 byte. 1 byte is 8 bits. So I'm gonna have 8 one, right? 8 of them. I'm gonna have 8 of them on the input. And how many I'm gonna have on the output bus? So now it's going out the data for reading. Come on, how many I can have on the output here? So let's put output. So the data now is flowing in the other direction. This is the other bus of reading things, and this is my output. How many? I'm waiting for answers. Nobody's is sending anything. How many is my width of the bus of the output gonna give gonna have wires here? How many wires? The others are not with us. There's just 2 students here. Come on. We saw that the input gonna go with the bit here, 1 byte, 8 bits. The output now, if I want to read the data back, how many bits gonna be the width of this one? There's just 2 students who answered. 3 now. Okay, 4. Good. And they are all giving the right answer. It's 8. It's the same. I want to read the data. I want to read byte by byte, right? Byte by byte. So it's 8 bits. It's a 8 bits. Okay. That's good. So now I know that I have this input thing, that it's 8 bits. So this is the input. You see the arrow is going inside. I know that I will have also the output. That's gonna be how many? 8 bits. Now I know also that I have 1024 address. 1024 address. What is the how many bits I will have to be able to build this probability here for the addresses in each ship? How many? So the address bus, what is the width of the address bus in our example here? Please repeat the question. I know that I have in each memory bank 1024 address, right? 1024 address. To be able to get this probability of 124 address, what gonna be the width of my address here? So this is the address bus. What is the width of it? And here it's the same, right? So I'm gonna have an address bus. It's the same. It's 1024, 1024, 1024. So in each case, it's always the same width. But to be able to have this 1024 address of probability, What is the width of this address bus? Here. What is the width of this address bus? $32. Seriously. I have 1024. 128. Damn it. 4 kilobyte. Well, we have a good answer here, Harkirat. That's good. That's good. Yeah, Gurvir, I have 1024. So to get 1024, how many bits I need? I need 4 bits. Okay. $8,192. My God, Jagjit. Vegas 8. Gurvir, 4 kilobit. No. Kilobit, you are talking about capacity. I'm not talking about capacity at all. I'm just saying how many bits. 8 Malhar. Okay, let's go with it slowly, right? So imagine that I have this RAM here. So I will explain to you one simple example and I will ask again the question. So I have 1, 2, 3, 4, right? So I have 4 location on my RAM. It's not anymore 1024, right? It's not anymore 1024. It's just 4 locations. So I have 2, 3, 4. How many bits I can use for addressing this 4 location? How many bits gonna be enough for me? It's just 4 now. It's not 1024 anymore. 4 bits? So everybody is saying 4. It's wrong. It's just 2 bits. It's just 2 bits. It's not 4. It's 2 bits. Why? Because of if I have 2 wires, I can plug them here, both, right? So I'm gonna have 2 location here. Go in the second one, go into the second one, and this is the first and this is the second one, and this is the first and this is the second one. With 2 wires, I can have the 0, 0. I can have the 0, 1. I can have the 1, 0. I can have the 1, 1. So it's done. I have 4 addresses with 2 wires. So it's 2 power 2. Right? 2 power 2. This 2 is the 2 wires because I'm working with bits. Remember, 0 1s. So I have 2 probabilities. I don't need 4 wires. With 4 wires, I can have much more addresses. I can have 2 power 4 addresses, right? So I can have 0 0 0 0. So this is the answer for all the guys that they said 4 here. I can have 0 0 0 1. I can have 1 0 0 0. I can have 1 1 0 0, and so go on and so go on till I'm gonna have 16, right? So I'm gonna have much more addresses with 4 bits. Much more addresses with 4 bits. So having 4 location, I'm looking for 4 addresses here, just 4 addresses. I can do them with 2 bits. 2 bits, 2 wires. I have the probability 0 0, 0 1, 1 0, 1 1. It's done. I have the four addresses here. So this one will be the 0 0, this one will be 1 0, this one will be 1 0, and this one will be 1 1. And it's done. Right? So I can now map a memory bank of 4 location, of 4 addresses using 2 wires. Now let's go back to our example here. I have 1024. With how many wires I can address this 1024? So what gonna be the width of my addresses bus here? By 32. So what is well, let's take the calculator, right? What is the probability with 32? So let's see it. 2 power 32. I can have 4 gigs, right? 4 gigabyte. I'm not looking for 4 gigabyte. I'm looking for 1 kilo. Rise power 10. Good, good, good. Rise power 10. And also Davinder said before that it was 10, right? So it's 10, 10. 2 power 10, I will have exactly 1024. Here is it. 2 power 10, 1024. So the width bus of addresses here will be 10. This one is 8 bits and this one is 8 bits, but this one gonna be 10. Vikas, it's not 8, it's 10. 1024, right? 10. So I'm gonna need 10 here. I'm gonna need 10 for addressing. It's gonna be enough. 10 in this case, in my case, it's gonna be enough. How many time I will have 10? Four time. Good. So how many time I will have 10 is 4 time. In 4 different location, I can have this 10, 10, 10. So I need also to map these 4 different locations. So this is a wrong way to do it like this. It's gonna be a little bit different now. But let's do it properly. Right. So here I will have the input data, 8 bits, right? 8 bits. Okay. And now to put things also, or to read things also, I will have 8 bits of data going outside. Right. And I will have the 10 address, right? So let's do it better. So we'll have also the output. And I will have the output here of data. So input, output, 8 bit, 8 bit. That's good. And the address will be also 10. So we'll have here my address bus that's going to be 10. Okay, this is my address bus. Several bits, several bits, several bits, several bits of 10. But I'm going to need something weird here also for the addresses. I need to select which chip I need to go. So the addressing is much more complicated. It's not just about my 1000 address. I need to say I want to go to the 1000 address in the chip number 1 or chip number 2 or chip number 3 or chip number 4. So I have 4 probabilities. And we saw before 4 probabilities how many bits I can use to have to describe 4 locations. How many bits? We just saw it before, 4 bits. 4 location, 2 bits, right? So 2 bits. So the addresses in all here, it will not be just 10. They will be 10 plus the 2 bits that I can describe this chip by 00. This one I can describe it by 01. This one I can describe it by 10. And this one I can describe it by 11. And after, I will have the other 10 bits here that they will describe the real address after, right? So my width bus of address here will be 12 in this case, will be 12. So I'm going to use 2 to describe which chip before here, right? So this one going to take the 10, but I'm going to need a multiplexer here. So I call it multiplexer, right? So for my bus address, so this is all the width of my bus address that I have 12 here, but it's going to multiplex on the first 2 bits to say which chip first I'm going to go here, or use this, or use this, or use this, right? But just using these 2 first bits, I can select I'm gonna go here. So this one basically will be here the address in reality. So this one is 01 and this one is 10 and this one is 11. Okay, so I can say that I'm going on 00 in this one, multiplexing these two extra bits here that they are 12. All I need here for the addresses is the 10 bits that they are after these two bits. All right, the 10 bits that they are after these two bits. That's it. Now, of course, it's the same way. All those are multiplexed. So instead of 8, they're going to use 10, 10, 10 also for selecting the chip. There we go, somewhere like that. So they will be all in the same bus here. Several bits, several bits, several bits, several bits. And of course, at the end also, we're going to have some instruction, right? Read or write, that final bus on those chips here that gonna say we're gonna enable this bus of the input, or we're gonna enable this bus of the output. So if this one is 0, the input will be enabled. If this one is 1, the output is enabled, and so on. That's it, right? And this one will go also everywhere. But just the width is just 1 bit here. It's not several bits anymore. It's just 1. So we send that signal of 0, 1, and we're going to enable which bus here. So okay, so we select the chip here. Okay, let's go to 1, 0. Okay, 1, 0, we're here. And after the 10 bits, going to select which location we are here on this between 124. And we had here, for example, 0. So this bus will be enabled and the data will go out. And this is a memory chip of 4 kilobytes. If we take this principle and we double it on the other side, we have 8 kilobytes. Right? So it's just a small chip here for a small memory amount. All right. Now we have the bandwidth also is the frequency that it's handling here for how many cycles we have in each nanosecond, each second, each hour, each whatever, right? So proper to the time, how many cycles we have of sending, reading things. Okay, that's called a clock, and this is the all the process of sending things here, passing through this memory controller. So imagine if I have this and I have this now also. So this I will double it in another DIMM. So this is a DIMM here, and this is a DIMM here, and now in between I will have a memory controller. It's another kind of this multiplexer here, but a little bit bigger and handle other things, right? Handle all the traffic and the speed and the frequency between this and the motherboard and the CPU in the same time. Oh, this is my memory controller here. Okay. Now, if I double again this concept, again, I will have a second memory controller here if I'm working on dual channel. So let's say I'm working in dual channel. Here we go. So they will go to the same bus here and they will go to the CPU after. Of course, here the cache is L1, L3, L something and go into the CPU, right? So this is a part of my motherboard dealing with the RAM. So if I have 8, 16, 24, and 32 kilobit of memory, it's not that much. Well, now if you're gonna make more addresses, you can have much more bigger RAM. So I can have 4, 8, 12, and 60 gig of RAM if I'm putting each one here 4 gig of RAM instead of 4 kilobit. Okay. By why? By the addresses, using much more addresses. So the width of the bus here will be 32 instead of my 12. See the 12 here? I'm going to use a 32 with a multiplexer with mini chips and so on and so on. All right, so you guys, I hope you have now better conception of the memory, how it works in your motherboard. So dual 3 channel. some further PCI explanation. Okay, so let's take a break, right? I'm a little bit tired. Let's take 30 minutes of break here. It's 10:20. 10:20. We're gonna take 10 minute, 30 minutes. Sorry, 30